Welcome everyone to the next episode of Cloud 101, Realizing the True Potential of Cloud Media Operations. Thank you for joining me today. Dan, I'll just checking with you, make sure everything looks good. Excellent. So today we'll be doing a case study on playout and talking about the three phases of playout migration, implementation, optimization, and transformation. So let's talk about migrating to the cloud. In this session, we'll be talking about migrating a playout solution, and we'll be talking about how we optimize that solution for the cloud. And finally, we're talking about transformation and reinvention and how we made that solution really leverage the cloud and take advantage of everything that's possible in the cloud today. So before we begin, let's talk about what is playout. Playout takes live and pre-prepared file-based content and assembles it in a ready-for-air signal. Live includes live feeds, live data, data-driven graphics, and live captions and subtitles. Pre-prepared includes programs as files with captions and subtitles, and graphics including logos and promos. And additional processing is often required, including things like format conversion, up and down conversion of video on inputs and outputs, adding ratings, watermarking, things like Nielsen in the US for ratings, multi-channel audio processing. You might have different languages. You might want different languages on different outputs, and multiple output streams for distribution. So playout starts off being simple, but it turns out can be a fairly complicated thing. So what does a playout system look like? Well, originally, playout was built out of a lot of purpose-built components. And then about the middle of, I don't know, around 2005 to 2015, we started this migration towards what we called channel in a box. It was integrated playout. It was running playout on off-the-shelf servers instead of purpose-built hardware, and it was putting all of it as software into those servers. So all these different functions were put into that server. Basically, it created what was called a channel in a box, things to fetch media coming in from external sources and cache them on that server, to play out those files, media management, ability to create and render graphics real time, to process live inputs, things like DVEs and mixing, and then also all the process we talked about. And finally, we output this in various formats for broadcast, and we can also record the file. And typically, attached to every one of those systems is a thick client. So you connect into that and you're actually running that engine directly. So, and then behind that, and over here, I'll show you just to be clear, what we were just talking about, the engine, are these components over here. This is the channel box cloud engine. But in addition to that, we have things like a database that runs the system, that manages all this, and there's usually a primary and a backup and a redundancy management, so it's like a SQL database often. There's the ability to have an ingest record function, so other servers that actually sit there and record feeds coming in for later playback. And then there's a management system that manages multi-channels, manages video routing, manages redundancy, so manages failover of different systems and keeps an eye on everything with a watchdog. And there's a media management server that manages all the media, keeps the library intact, knows where everything is, knows what's needed where. And manages also the file ingest and QC. So every file that comes in has to be conformed, make sure it works correctly, QC'd, and potentially also transcoded to the right format. So these are all the sort of moving pieces and parts we have to create a playout system, circa, let's say, 2015, 2016. So when we want to migrate to the cloud, the beautiful thing is this is actually software running in commodity servers. So we're pretty much all the way there, right? Well, maybe. So we have basic integration that we need to do to get it to work in the cloud. First thing, of course, this has to be all IP. So if there's SDI, we have to replace that with the ability to do IP video on the inputs and outputs. Often there's multicast used to connect all these different components together to make them aware of each other, and for control, that has to go away. We also want to use the cloud native database and not just separate SQL stacks, because that's expensive to run your own database engine when it's already plenty running in the cloud you can choose from. And we have to use native cloud transport protocols and formats, because running video up to the cloud and through the cloud is not the same thing as running it through a network on your premises. And so we need to modify the signals to make that work. We want to use native cloud storage. And of course, now we need a user interface that's appropriate for a remotely connected cloud system. So we migrate the system. And the first thing I said, we of course want to get rid of is start using cloud database, use a native database service. That's a really easy thing to do often because it's just another SQL database. We also want to make sure that the feeds coming in are protected to be able to transit through a cloud, because the cloud and the signals through the cloud is often public internet, or at least a network that isn't over provisioned and non-blocking the way a private network might be in a broadcast facility. So here we use things like ZXC, SRT, and RIST, which use a protocol called ARQ to help protect those signals and make sure they transit across these unmanaged networks without losing data. They add a little bit of delay, and they also resend signals when there's something that doesn't make it through during that delay. And we add cloud storage capabilities. So in Amazon, that's called S3, but it uses a different protocol than your NAS uses on in your facility. So you need to be able to adapt to using S3 in the cloud, your system. And of course, to be clear, these are some things your cloud playout vendors are doing for you, or if you're a cloud playout vendor, this is something you need to do, of course, from your existing system. And we need to also then build our application to run on the cloud servers. Typically, for example, that's an application machine instance that we run in Amazon. So it's actually an image of the actual instance we want to run that we can then launch on that server. So that's my cloud playout. And of course, here's the cloud playout engine here on the right that we talked about a minute ago. So we have multiple engines that all this is connecting to manage all the channels you want to run. So that's basic lift and shift on the output side. On the engine lift and shift, it gets a little more complicated. Obviously we have some of the same things. We need to support native cloud storage again, that S3. And that's also not just for source material, but also on the output side. And then we actually want to keep content in EBS storage, which is not in the server itself, but shared amongst multiple servers so that it's high performance, it's able to be drawn without any buffering or latency. And also, if you tear down a server instance and spin up another one, you're not having to repopulate all that content. It's in that same storage. So that's a key thing we do there. We use cloud transport again to get the signals into that engine. And one thing we're going to probably need to add is a frame synchronizer. So typically in your on-premise systems, all your signals are synchronized. So your cloud system doesn't need a frame sync coming in, it just needs a gen lock. Maybe it's got a 1 or 2 line buffer. But in the cloud, we're going to want a frame sync. So we need to actually make sure the cloud systems have frame syncs built in. And we're also want to be able to control those routing sources over IP as opposed to SDI routing, and certainly not serial control either. We need the same cloud transport on the output side and the same cloud storage we talked about a second ago. And we want to replace that thick client with a web client. And that web client is going to give us the ability to run the system from anywhere through any web browser. So that's basically what we want to do. So now we put all this together. So we put that engine back with the rest of the system we had here. And this works, right? Now we're running in the cloud, we're running playout in the cloud. This is awesome. But it's expensive. We've got a lot of things running. We've got each of these servers running every time. We've got these ingest servers running all the time. We're running graphics instances, which are expensive. They're about $820 a month or $10,000 a year just for the engine, just for the server running each of those playout engines. So how do we optimize this? What if I told you we could get the cost from $820 a month down to about $50 a month or $600 a year to run this system? Well, stay tuned. Let's look at how we do that. So the first step to optimization is orchestration. And orchestration is about where do you want to run your service, whatever that service is, and how do you want to run it and when you want to run it. So it basically says instead of just leaving things running full time like an ingest server or a media manager, we're going to run these things only when they need to run. We're going to run them the right way. We're going to run them in the right part of the cloud where it's optimized to run that. And to do that cost optimization, we need to understand the costs of running in the cloud. And we need to make some technical decisions about how to optimize those cloud costs and some trade-offs. So let's look at how we might do that. So for media workflow optimization, we already are using the cloud-based database and cloud transport. We did all that. But I've got these things like file ingest and QC, and there are native processes in the cloud I can use to do that. And that means not only am I not spinning up my own servers every time I want to do that and waiting for that to happen and spending cost and time and paying by the hour when something might only take 15 minutes to do that. I'm actually paying just for the workflow that needs to be done to do those things. but I'm also not even having to manage that orchestration. So that's a big plus if I can move to native file ingest and QC and transcode services, because enables orchestration automatically, and all means I'm paying for the actual processing time and the amount of processing I'm doing versus the time I leave a server running. I can also use things like S3 change notifications to trigger file movement, so I know when something's arrived and new files landed in a watch folder. I don't have to sit there and keep polling with the server. I'll get a notification that'll trigger a workflow. Maybe that workflow is even running serverless. So now I don't actually need to run these things at all in a server. They're all running serverless. And that's really the key thing here is I'm using Lambda to run file ingest, QC, and transcode. All these things are happening and they don't need a server to run in. So now I'm saving all that cost. That's a good start, right? Um, I can also do my ingest optimization. So now I'm going to run my ingest recorders only when I need them. And maybe I'll even run them in spot instances because a spot instance is as little as 20 or 10% of the cost of a permanent instance. But I can run spot instances for 1 hour or 6 hours, so I know it'll be running for the entire duration of that ingest record without worrying about losing it. So it's a perfect application for that. It didn't used to be you could run spot instances that way, but now you can. So that's a really strong benefit. Um, So we'll do things like that. The other thing to think about is redundancy. So typically you build an on-premise system and you have a primary and your backup server or an A and B server or red and blue and green, whatever you want to call them. You have a pair of servers and they're always running together. One is primary, one is standing by in case the primary fails over. Well, at different times a day, a channel has different value. In prime time, you probably always want to run 1+1 on your main channels. But in the middle of the night at 3 a.m., maybe you can run one backup for a whole slew of channels. And if you go down for 15 seconds while it switches over to supporting that particular channel where another instance failed at 3 a.m. on a DigiNet channel, is that a big deal? Is it worth spending, the tens of thousands of dollars to have the 1+1 redundancy 24/7? That's a debatable question. But nice thing is in the cloud you have that option, and you can make those informed decisions. So having a redundancy management system that gives you different level of resiliency depending upon the channel, the value of the content, the time of day is really key to really saving money. On the playout engine, we also have other things we can do to optimize. If you look at this, we have a lot of services running inside that playout engine, and a lot of them are bursty. A lot of them don't happen all the time. First off, this is no longer the channel in a box, right? This is a playout engine. We've changed this already, the workflow here. But the first thing we want to do is move things outside of that engine that can be transient and run elsewhere. So I don't need those file triggers. Actually don't want the playout engine to manage as media anymore because it's not going to a shared EVS storage anyway. And I also can put the graphics engine outside because I don't need to have graphics being generated real time in the playout engine because most of my graphics are not real time. And a lot of times that graphic system is just sitting there, spinning wheels, using CPU cycles, and not doing anything, but costing me money. And in the cloud, that matters. It didn't matter so much when it was on-premises system. You always had to have that there anyway, so what the heck? But in the cloud, if I can offload that graphics to a cloud processing as a service and just have that graphics arrive just in time when I need them into my system, I will save a lot of money. And it also allows, and to give you an idea, that means I can then move from a GPU-enabled instance to just a CPU instance. And that's a 60% savings in the engine costs right there in the instance that this is running on. So that's a big saving. So what are the principles of orchestration? What are we really talking about here? It's about what runs where and how. So first thing is, in the cloud, there aren't just servers. There are kinds of servers. They're all different sizes, different capabilities, but they also can be run different ways. So you can run an instance nailed up all the time. That's your reserved instance, and you can reserve that instance for 1 year and 3 years. You can run it as bare metal, all these different ways. You can also run it on demand, and that means you're paying by the hour and by the minute for running it. You can run it as spot. Spot's pretty cool. Spot instances are where you actually go and you bid on excess capacity that's not being utilized at that moment in the cloud, often between 80 and 90% savings over that on-demand price. So if I have an itinerant workflow, like maybe a transcode or something else, instead of spinning up an instance and paying for it for an hour and only needing for 15 minutes, I can do that in a spot instance, and I can also do it at a fraction of the price. So this is really key. And the last one is Lambda, which is what Amazon calls serverless. And I apologize for using Amazon terms a lot, but I do a lot of work in Amazon and they're top of my head, so forgive me there. But the the Lambda is really cool because it's serverless. You're not even running in a server. You're basically taking your code and throwing it at the cloud and saying, run this for me. Run this process and give me back the result. Run this transcode, run this media QC, run this file mover. So if I can do things in Lambda, then I'm only actually paying for the CPU cycles I actually consume to run the workflow and not for the time it takes to reserve and spin up an instance and have it running and check it and then load my application, then run my application and do this and then check it and then, okay, everything's fine and finally tear it down. All that goes away. And plus, I'm getting 100% utilization because when I typically run my own server, I'm not going to run it at 100%. I'm going to run it at 20 or 30% to make sure it works well. So I'm not really getting the full capacity of it. The other thing is GPU versus CPU. GPUs are expensive. You can probably thank blockchain for that and all those cryptocurrencies because they're the ones who are stealing all the GPU cycles. And then all the gamers are also running GPUs. So you have a lot of competition for GPU instances out there. You can read stories about what people are doing to get hold of GPUs these days. So if I can run in a pure CPU instance instead of a GPU, I'll save a lot of money, right? And I can still get the same instance sizes, the same number of cores and stuff. Native services versus launching an instance run service. So think about that. If I can run something in a native service, I'm only paying for the CPU cycles or the certain workflow that it takes to do that versus actually paying for the entire infrastructure, whether I'm waiting for actually the process to happen or some other part of that. And it's really optimized also. So understand these cloud costs and trade-offs. For example, one of the cloud costs and trade-offs is, I'm going to be able to choose whether or not I want to output over here at H.264 or HEVC. Now, HEVC is a far better compression algorithm. You get, two times or better compression density with HEVC. So therefore, I'm going to pay less for those egress costs. But I'm also going to need a server with more performance. I'm going to maybe need more cores. So if I don't have any extra cores, I might need to spin up a larger server. So I have to look at that cost versus the cost of the transport and make that decision. If you're an engineer like I was growing up, looking at this from a business perspective and making all these cost calculations is perhaps foreign to you and difficult, but it's an essential part of really getting to get the cloud to work for you. And that's what I really want to get across in this presentation, is showing you how we're going to rethink entirely how we do playout in the cloud with an understanding of these costs and how transformative that can be. So let's take a look at what the result of this, and this is a real world case. This is actually, I showed this on the last presentation too, so you may remember this, but this is standing up two similar playout systems. One is cloud native, one is traditional using lift and shift, running exactly the same workflow. And the blue one is the actual Amazon cost for the lift and shift, and the red one is the actual Amazon cost for the cloud native. And as you can see, it's somewhere between 12 and 15%, the cloud native, the cost of the lift and shift one. So that's a significant savings. I mean, that's basically saying I can run 6 to 8 times as many channels in the cloud native as I can in the lift and shift one for exactly the same price. I'd like to get 6 to 8 times the same paycheck too. Tell my boss that for me if you ever speak to him, will you? So anyway, so how do we do this? How do we get this kind of real optimization? And can we really optimize this any further? Because at some point, there's that law of diminishing returns, right? We're going to keep putting more and more effort in to try to figure out how to really optimize this. But at some point, we're really just sort of making it too hard to use and get this optimization. We're not getting enough benefit. But the other thing is, if you look at the last models and what we've been looking at so far, are we really leveraging the unique capabilities of the cloud? Are we really matching cost to consumption across the board? Have we built something that can really scale on demand? And are we really leveraging massive CPU and storage capabilities? Because that's what the cloud really brings to the table. So what if we just abandon all the traditional cloud architecture right now and reimagine this playout for the cloud? Well, the first step, I think, in doing that is understanding what the cloud wants. And the cloud already has native technologies, right? Native IP and cloud technologies. Things like, for example, HLS, uh, HTTP linear streaming is how we actually stream video today when we watch video online. We don't stream it using transport streams. Adaptive bitrate to make it work across an untrusted network. Um, we leverage the cloud's unique capabilities, massive compute, connectivity, storage, and scale to be able to spin up as needed, spin up at scale, real-time After Effects rendering, affiliate branding and things like that we might be able to do if we really leverage those capabilities correctly. We also want to have things like on-demand and serverless to really use that properly. So we're paying for consumption and not capability of servers just sitting there not doing work at that moment. And we want to tear down some silos. We want to get rid of the silos that segment playout and production and OTT and delivery and all these different functions, because if we build these end-to-end workflows correctly, we'll really streamline things and make it easy for content to get from the beginning to the end of our workflow, from creation to screen, and metadata to make it all the way through that same workflow. So this is what we really want to do. And if you look at where we've been coming for years, we've had this problem where you know, if you've been a traditional broadcaster, transmitting transport streams over satellites and antennas, and OTT came along, watching TV over the internet, it was a whole different workflow and required a whole different set of technologies. And so we were living in this bifurcated world where we had two different systems we had to manage and two different workflows and two different teams. We even started calling, one team broadcast engineering, the other one digital, as if everything wasn't digital. It didn't make a lot of sense, right? So let's talk about how this also helps us get rid of those silos. So also, why is playout expensive? Well, the first thing is it uses real-time linear transport streams. And and uncompressed pixel processing internally too. But those transport streams are very particular. We'll talk about that in a second, with precise timing and cadence requirements. We also have a problem with bursty workloads. So suddenly we want to do graphics and DVE moves and things, and that's a bursty part. We also have noisy neighbors. If you're running in the cloud, you're often in a shared VM environment with another system running parallel with you in that same server, maybe multiple other customers running in that same server. And while you're isolated, and very well isolated perhaps, there's always that risk that just something that's happening in that CPU and in that memory, so there's a little bit of jitter in that transfer stream that causes a problem. And this is one of the issues in running the cloud we need to understand and figure out how to work around. So what if we could get rid of the rigors of transport stream precision, and we would need to have this excess CPU capacity? How can we really do that? Well, first, let's take a look and understand what we're talking about here to make sure we're all on the same page. So how does OTT work without the problems of transport streams over IP? A transport stream is a chunk after chunk after chunk of video in very precise timing that's delivered, traditionally over ASI and over RF and now over IP. But there's this expectation of perfect timing, no retransmission, no jitter, and that this arrives. That's really hard in an unmanaged IP network, right? In fact, as we started to build live production systems, we went to something called 2110 as a standard for uncompressed, which is even more rigorous, which makes this even harder if we ever think about using uncompressed in the cloud. And we'll talk about that another day. But OTT takes that same compressed video and breaks it into chunks, often along the iframes boundaries, and converts it into short file segments that are saved as file segments. And those file segments are actually sent as file transfers to your player and are stitched together by the player for linear streams. So the player is actually requesting file segment after file segment. And to know what file segment it needs, there's another file called a manifest that it receives. It tells us about all the file segments that it's being sent right now, other file segments that are available at different bit rates if it's having trouble getting files, and then what to request after that. So this is how that works. And basically it's HTTP file transfers that are being stitched together by a player. So we don't care about jitter. We don't care about sending a whole bunch of packets and waiting a bit and sending a whole other bunch of packets, because the player is going to buffer all those, assemble them, and play them back. The player is doing the heavy lifting now. And what's happening at the other end is just a file server with the files sitting there. It's pretty straightforward. So if we imagine cloud playout and we move away from transfer stream to HLS at the source, how does that change this? Well, first we get rid of all those timing requirements and precision. Now I don't have to worry about the server running precisely and running constantly, and with lots of overhead to make sure it doesn't have to worry about noisy neighbors and such. And it certainly simplifies transport across unconditioned networks. I might not even need to worry about reconditioning the feeds with cloud transfer protocols. So if I took my playout engine that we were talking about, let's first start and make this file only and remove the live components for now to simplify this discussion. So we'll start with a file only playback engine. If you think about a lot of cable channels today, 95% of them are file only playback. They just play back files after files after files. They're not news and sports networks, they're the movie channels and other things, right? Perfect example for something like this. So we're going to get rid of that output that we were sending as streams, and we're just going to take this output as HLS and send it right here to the storage. And so when you run the playlist, it writes the output to an HLS file. And that HLS file is actually a live streaming file. So it actually has metadata that identifies it with timestamps in the air schedule, so the player knows when it's supposed to be getting something. You're not watching something for tomorrow, you're watching the right thing for right now. So there's our playout file only playback engine. And what's really cool here, as we'll see, is we can actually generate these ahead of time, right? Because these are files. And we know as soon as the playlist gets published, we can actually run this and generate this. Okay. So now I can run this and build this anytime. That means I can also QC it ahead of time. I can prep it ahead of time. Um, it also means I really don't need to have redundant servers because I'm doing it ahead of time. So I can check it. I don't have to worry about having two systems running in parallel. Well, there's 50% savings right there. But the engine can also, when it runs this ahead of time, run this at CPU speed and not real-time clock because it's creating a file, not a transport stream. So it's just like when you render in an editing system, it runs as fast as it can and it burns up every cycle of that CPU trying to get that file rendered. And that's why this would run. So what's really cool about this is that instead of running my CPU at 20%, I'm going to run it at 100%. So now it'll take the fifth of the time to do this on average that it normally takes me to do a playout system, maybe even better. So if I compare the costs here of this, I'm going to get 100% CPU utilization, not 20%. I'm going to use spot instances. That's going to save me up to 90% over paid for instance, full reserved instances. I'm not going to use a GPU. That's going to save me another 50%. And you multiply these by themselves, well, G3.4x large is going to cost $820 a month to run. A C5 4x large, only using 20%, so running a fifth of the time, it's going to cost $58 a month. That's 93.4% savings. And I can cut that again in half by not needing parallel redundancy. So now instead of having what's that 6.6% of a GPU cost, I'm now at 3.3% cost of what we started with our lift and shift GPU. So we've gone from $820 a month to 3.3% of that to run playout. Or let's just round it up, make it 4%. Okay, good enough. I'll go for that. But that is substantial savings, right? And we really haven't given up much. We really haven't. And the neat thing is it's really reliable because the only thing that's actually running during playout when we're not live, well, nothing. It's just the file sitting here in this bucket. The HLS file is ready to be pulled by a player. The other neat thing about this is exactly the same workflow we want to do to create VOD and OTT. So now we have a unique and unified workflow across all of our outputs, VOD, linear, broadcast, OTT. So this is the model, right? I've got my pre-rendering engine here. It's writing to a file storage here. OTT HLS files manifest, and now at the other end, and wherever the receivers are, there's always a receiver, right? There's an IRD, there's something, a player. Well, this is a player receiver, and it actually takes that HLS and it can convert it to a transport stream at the other end if it needs to, or even 2110 or SDI. It can also do regionalization, localization, ad insertion, logo insertion, and even have a disaster recovery cache if we lose connectivity, because it can just cache those HLS files, or we can push files ahead of time to it for it to play back if it loses files. So we can even actually push these files ahead to that player instead of actually leaving them in the cloud and streaming them real time when it's needed. So there's a lot of intelligence we can put in here to really make the system resilient and really make it inexpensive at the same time. So we looked at that, okay? But now let's talk about how do we do live feed. So how do we do live feed integration in here? So there's my file-based playout system sitting up here. That's basically turned off right now, right? We've already pre-rendered our files. They're all sitting here. This is being streamed to air by the player, and this isn't running at all. We've managed to do that. But now we want to go live. What do? We spin up a live instance, a spot instance, on demand, whatever we need to do here. And that live instance is pretty similar to that original, lift and shift instance we looked at. It'll be optimized. But fundamentally, it is that instance with built-in graphics, doing all this and everything else we need to do and stitching together to create live event. But we still output is that same HLS. That's really the key here. We're going to output that same HLS here, and then all it does is the manifest says use these files, not those files. So the player is just being rerouted to look at the HLS output coming from the live. That's the new model. So we output the HLS and manifest as we just showed. The instances are only running to pre-render and when live, so there's nothing running most of the time at all for your playout system. I mean, nothing at all. It'll add 2 to 4 seconds of latency for live throughput for low latency HLS chunks and delivery approximately, but also we're avoiding the latency of cloud transfer protocols, which helps offset some of that. We can preview content before air. We have increased reliability, less moving parts, and it's much simpler to scale. And we've created a unified workflow across VOD and linear channel delivery. So we really managed to streamline that, which is something we've been wanting to do for a long time. And we've also simplified creating multiple derivative output streams and edge branding using the same server-side ad insertion technologies we've been using for OTT for a long time. All while actually saving between 90 and 97% over full-time redundant GPU instances. That's a huge savings, right? So look at that. Those are the 3 models. So lift and shift. This is where most customers are today, making it work, trying to make cloud playout work, and using a lot of familiar technologies and familiar systems that they're comfortable with. And then they go and we optimize those, and we can get 40 to 80% savings if we really do it well. But if we really reimagine it, we'll go from being half the price of lift and shift to 3% of lift and shift. That's a huge difference. And that's what's possible. So this is just one example of how you can take common media workflows and reimagine them for the cloud. Here we use something that's extremely persistent, a 24/7 linear playout channel, and we reinvented it. We matched the cost to consumption, only running services when we actually need them. We created scalability with better performance and reliability. We unified legacy playout and modern VOD and OTT workflows into a single solution, and we're running all this for substantially less than an on-premises system cost to operate. Less than on-premises. You don't often hear that when you talk about going to the cloud, right? So let's take some questions. Dana, what do we have? Okay, I've got a couple here. Adam asks, can you explain those savings again? How did you get that? All right, let me pull up my notes here because this is going to be a little more complicated. So in the beginning, we set up the G3 4X large instance, which is a 16-core server for playout. It's $1.14 an hour or $820 a month at on-demand rates. And you're going to be able to adjust those rates by having, 1 year and 3 years or other things, but we're just going to stay with on-demand rates for this calculation here. Now, if I move my graphics outside and I get rid of needing a GPU, or I learn how to do graphics without a GPU, I can move to a very similar server, a C5.4X large. It's also 16 cores, similar CPU, but it's 68 cents an hour or 60% less than the graphics instance was. So immediately I get 60% savings. That's the basic lift and shift optimization, is moving away from expensive things, especially because not every channel needs fancy After Effects real-time graphics, right? Very few do. And to be spending the same amount of money across all your channels is crazy. So then I can also move this to this OTT HLS file-based delivery workflow as opposed to transport stream over IP workflow. And I can do that by running an instance, and I can spin up spot instances where I pay for it by the hour and I buy the cheapest ones that are out there on the market. So now that goes from 68 cents to 37 cents an hour, another 55% savings over that C5 instance we just mentioned a minute ago. But I can also get 100% utilization of that server when I move to that HLS workflow because I don't care about creating those transfer streams. I don't care about things that might cause the process to speed up and slow down as it gets more involved or gets simpler. So now if I'm only using that at 100% versus 20% utilization, I should also theoretically only have to run it for a fifth of the time. So now it's only going to cost me $53 an hour. So that's another savings there. So that $53 an hour is 6.6% of what the GPU cost at 820 bucks a day, 53 bucks a day rather. So and then I can eliminate that 1+1 redundancy. Well, that'll get rid of 50% savings right there, right? So it's not 50% savings. So now I'm down to 3.3% of the original GPU costs. Of course, your mileage may vary, right? Everything's different. None of these are exact. You might get even better than this. And we didn't even talk about the other workflow and system management savings we have on top of that, all these things we didn't have still running. So there's other savings that are still adding into that, but this one was really easy to measure. And each cloud instance, how it could go to 3.3% of the cost of the original GPU instance that I was speccing and standing up. So thank you, Adam. I really appreciate that. I think I got time for one more question, right? Okay. Michael asks, is this available today? Oh, good question. So we're just starting to see this capability emerge on the market. I really don't have a good read on what vendors are really able to deliver this right now. I know a few have talked about this and have some ideas, but whether they've actually gotten all the way down the path, I'm not quite sure. But I'm sure more suppliers will see the light and we'll start seeing these emerge. Maybe some of them will see this presentation and get some ideas, some traditional vendors, and begin to understand the value of being cloud native. I also expect that customers will become more educated and begin to look for this kind of innovation and not just look for lift and shift. And in the end, this is just but one example of how the cloud opens up new doors of possibility once you truly understand it, right? Both technically and from a business perspective. So I thank you for joining me today. We're just at the beginning of this transformation, and I look forward to bringing you more stories about how the cloud is changing the media and entertainment industry. I also encourage you to come join me at the SMPTE Cloud Media Club, where we discuss ideas like this every month amongst fellow media professionals who are working in the cloud. Thanks for watching, and I hope to see you soon, maybe even in person, as we migrate to the new normal. Until then, be safe and be well. Thank you.